Hello everyone, this is Mono Bunny, just giving you a quick video demonstration of our CPLD based Atari 2600 VCS cartridge bank switcher, in this case in the 8K/F8 ROM bank switch format. So here you can see my general mess of wires that I'm using here to basically test bench the programmed implementation of our CPLD chip here. Now we have two LEDs, and one of them is already illuminated for us here after I hook this thing up to USB power for testing. And this red one right here, this is our clock LED. So this is hooked up to a resistor. It's hooked into an RC, it's tapped into an RC circuit basically. And if you look at our schematic that we're using, and this schematic is of course originally by Joe Grand himself from Pixels Past, but it's publicly freely available for our purposes, so that's what we're using here. At some point I'll be translating it over to my own schematics for my own practice and practical reference, things like that. But so as we can see here, pin 1 is the clock input pin, and here is the RC circuit. It has a calculated 220 nanosecond delay due to the capacitor and resistor component values selected for this RC circuit. So you have a 2.2K resistor and a 100 picofarad capacitor. And so this is our RC circuit that basically winds up oscillating fast enough to generate a clock frequency. And so it's not on here on the schematic, but basically for our test bench, I have that LED basically tapped into this RC circuit. And so as we're manually pulsing data from pin 1, which is basically this white one here, as we're pulsing the power source on this pin from high to low and back again, this red LED will cycle back and forth. We have one more pin, LED, and that is this yellow LED. Now that's hooked up to O12 on the schematic, so it's tapped into O12, and that's basically our A12 bank switch output here on the F8 bank switch scheme. So that goes all the way back to pin 20 of the CPLD. And so how this works is basically when a certain trigger address is reached, the combinational logic in this programmed into the CPLD basically says, okay, the appropriate address conditions have been met. Now we're gonna set O12 to high, and when O12 is set to high, that basically gets sent to the EEPROM, and as long as the program code on the EEPROM follows the appropriately implemented bank switching address schema, when that happens, the EEPROM logic should basically cause the processor to be jumping to and then appropriately reading code at that newly bank switched address, so on and so forth for other bank switch scheme implementations. And so basically we can demonstrate the clock signal here. Let's see if I just so we can put this here. So for example, if we take this, 2, 3, 4. Yeah, so if I put this pin here, we get this to watch this. We get to watch the clock pin basically go, basically cycle. And why that's happening is because we basically changed one of our pin inputs. I believe it's number 4 in this case. So pin 4 would be like A1 on the address bus, basically. But so by changing that address from low to high, we've changed the state machine, basically, and this basically causes a clock cycle to pulse. And we can kind of look at the Kupel code to kind of see how that works, basically. So the clock out basically changes depending on the combinatorial state of, for the most part, the first 2 to 3 or so different elements. So basically, you know, if you're seeing A0 through A2 or some combination being toggled, that's basically the sign to have, clock out basically change its state. So if we, bring this back to low, then the clock cycle, then we see the clock LED light up again, vice versa. We'll bring the address to high, bring it to low, high, low, high, low. And so that basically lets us kind of simulate the clock pulsing. Now, it's a little complicated when we want to test the output of the bank switch, because we kind of have to remember what the logic schema is for the bank switch being logic true. But we can see it here because this is, O12.D, so, like the data, data of O12 as far as I can tell. Yeah, 14. Sorry, just checking some of the other output pins. Yep. A12. Yeah, so O12.D, we have, basically we want every address bit except for A2 and A1 to be high. So we can see here, if A2 and A1 and A0 are low, then we're not going to bank switch, we're going to be in bank 0. But if, every address except for A2 and A1 is high, in other words, all of these are high, and, and only A2 and A1 are 0, but A0 itself is actually high, then that tells us to have the bank switch trigger. And so we need to, ask ourselves, well, where is A0? Well, that's at pin 3, at least by the Kupel specification. So, and we see it here in the schematic. So we want to go to pin 3. And we can count, if we can just move these little cables, we can see it's this yellow one right here. Okay. And so this is high right now. Wait, do I have the right one selected? You know what? I don't. Sorry, my mistake. It's the green one that goes to pin 3. This green one goes to pin 3. Yep. Oh wait, did I get it wrong again? No, I was right the second time. It's green. So now when we set green from low to high, you're not going to see it light up instantly because we're between a clock cycle basically. But if I move this over here, sorry, if I do this and I move this over here and I let the clock, I let the clock cycle go high, and then I take pin 3. Sorry about the focus issue. And I move it over here from low to high. Again, you're not going to see it at first. You're between a clock cycle. Sometimes this works, sometimes it doesn't. It seems to depend on what order you do it. So let's see. Let's look at this again. We need A0 and A3 set to 1. So where's A3? That's pin 6. So pin 6, let me look at this. 1, 2, 3, 4, 5, 6. That's this yellow one, which is set to high. Yeah, there's something here that I'm missing. Oh wait, you know what? A2 and A1, are those low? A2 and A1, A2 and A1. So those pins 4 and 5 are expected to be low. So in other words, this one is expected to be low. And here we go. So yeah, my mistake was I had A5 set to 1. So now that I have this going, basically, you can see now that when I move this pin from high to low and clock it, as the clock elapses, the change of the bank switch output changes. Likewise, when I change that pin again, you get to see this happening again. So hopefully that's a pretty good basic demonstration of how this works. If you have any questions, or if I didn't show it off well enough, please feel free to, to ask for some more follow-ups or more information. I do apologize for the kind of the little delay points and for any of the focus issues. I am recording this with a phone because I don't have any sort of professional recording equipment except for a decent microphone, but that wouldn't really work for these purposes anyway. And yeah, I just wanted to give off a very basic demonstration. I know that there's a lot of wires here. Most of them, as you could see, I wasn't actively adjusting. Most of them were just me setting the address pin statically to 1, with only a few being independently manipulated between 1 and 0. Again, just to test this clock and bank switch output logic. So most of these pins are basically just being here looking scary, but most of them are just, you know, hard setting the address inputs to 1 for testing purposes. So hopefully this gave you a good overview of how the CPLD works in our Atari 2600 game cartridges bank switch scheme. This is Monobunny. Thank you for watching my video, and I hope to see you again soon, working on some cool arcade retro video game goodness. Toodles!